Hello and welcome to Romeca Corporation's three-part tutorial on how to drive a conveyor motor with a VFD. In this series, we will discuss how to use a variable frequency drive, a VFD, to modify conveyor belt speeds without damaging the drive motor. You'll learn how to verify VFD conveyor drive system adequacy by checking required power versus available power and motor cooling capability if applicable at all relevant rates. This is part one of our three-part tutorial on how to drive a conveyor motor with a VFD. In this session, we'll cover an introduction to the topic and demonstrate why a knowledge of relevant rates is important. To watch any of the other videos in this series, click on the link in the upper right-hand corner of your monitor anytime during this video. Conveyors need power to work in a straight line. However, conveyor drives provide power by spinning. Therefore, we'll need to define terms such as belt velocity, drive pulley angular velocity, belt pull, pulley torque, motor torque. Throughout this presentation, we'll be referring to asynchronous AC squirrel cage induction motors, which provide nearly constant torque across a fairly broad frequency spectrum. Notice that motor rotor RPM is linearly proportional to power supply frequency, and that motor power is linearly proportional to the power supply frequency within certain limits, which we will define. Motor heat damage is the most common failure mode when AC motors and VFDs are misapplied. And how can damage occur? It can occur if motor stator wires draw more current than they're designed for, or if the motor cooling system cannot adequately dissipate the stator heat. Throughout this presentation, we'll be using imperial units such as horsepower, feet, inches, that sort of thing. And we'll be referring to what might be called standard US power supply, that is to say 460 volt, three-phase, 60 hertz AC power. To simplify the mathematics of this presentation, we're going to ignore asynchronous AC motor slip, which is in the ballpark of about 5%. And gear friction losses, which can also amount to a few percent. We'll ignore both of those things to simplify the mathematics. Let's take a real-world example. Here we have a conveyor that was originally designed to move 450 tons per hour of stone. The conveyor is 120 feet long, it's inclined, 36 inches wide, and it has a belt speed of 330 feet per minute. On the left, you can see a cross-sectional diagram that shows that it's not completely full. The red line indicates what 450 tons per hour would look like on a 36-inch wide belt at a belt speed of 330 feet per minute. Separately, we've calculated that the required belt pull to do this work is 2,178 pounds, and the required power is 23.6. Therefore, the conveyor was outfitted with a 25 horsepower AC motor, which was designed to run on a readily available 460 volt, three-phase, 60 hertz power supply. Now, what if we're challenged with slowing the belt down? Well, you can see the cross-section of the slower belt shows the trough is more full. However, spillage should not occur because it's still within the SEMA guidelines, Conveyor Equipment Manufacturers Association guidelines on fill factor. And we've calculated separately that the required belt pull is 3,760 pounds to move 450 tons per hour at 165 foot per minute belt speed. Required power, therefore, is 20.3 horsepower. Will the drive fail if we simply install a VFD and attempt to slow the belt speed by cutting the power supply frequency from 60 hertz to 30 hertz? The answer is yes. The motor will fail because available power is only 12.5 horsepower, whereas required power is 20.3 horsepower. During the next few minutes, we'll be looking at relevant rates, relevant powers, and how to verify drive adequacy. Relevant rates include such things as materials handling rate, usually expressed in tons per hour, belt speed in feet per minute, electric motor rotor speed, generally referred to in terms of RPM, revs per minute, and power supply frequency, measured in hertz. Relevant powers include these 5 things: required mechanical power, expressed in horsepower, electric power supply available, we'll use 463 phase 60 hertz, installed electric motor power, usually specified in horsepower, as in the example I just showed, and then selected electric power supply, what frequency is going to apply, and available electric motor power, what's available, what horsepower is available. We're going to explore how to check required power versus available power at all relevant rates, and we'll check motor cooling if applicable. We're going to examine VFD usage in 2 types of material flow. We're going to be exploring continuous flow conveyors, taking one conveyor and making the belt speed slower, checking the results. And then we'll look at 2 instances of metered flow. We'll take a belt speed which was set, and then we'll attempt to make it faster and check the results. In continuous flow, it's important to remember that constant material handling rate will apply throughout the system. For example, if conveyor A is feeding conveyor B with a certain number of tons per hour, the material handling rate of conveyor B is independent of the belt speed of B. So if we're handling 450 tons per hour at a belt speed of 330 feet per minute on A, we will also be handling 450 tons per hour on B at the belt speed of 165. We need to compare required and available power in the A case, and we need to compare required and available power in the B case. Let's look at A more carefully. Let's suppose that a power supply of 460 volt, 3-phase, 60 hertz is readily available, so we decide to select that as our design case. We've chosen to move the belt at 330 feet per minute. That's our belt flow rate. We want to move 450 tons per hour. And so we've made a calculation and we've decided to install a 25 horsepower motor at a certain electric power supply. Let's compare required and available power to drive conveyor A. If we install a 25 horsepower motor and it's designed to run at 460 volt, 3-phase, 60 hertz, and the power supply is 460 volts, 3-phase, 60 hertz, then the drive will not fail because required mechanical power is 23.6, calculated separately. The available motor power is 25. 25 is higher than 23.6. Therefore, this drive should run continuously, indefinitely. Now, if we look at the same parameters, except we want to slow the speed down, let's consider decreasing the power supply frequency from 60 hertz to 30 hertz so that we could set the belt speed at 165 feet per minute. We know that we'll be handling 450 tons per hour. That does not change. What electric motor power is available? Let's compare required and available power in the B case. If we've installed a 25 horsepower motor designed to run at 460 volt, 3-phase, 60 hertz, and we decrease the supply frequency to 30 hertz, we will have a failure because required mechanical power is 20.3 horsepower, calculated separately, but available motor power is only 12.5. 20.3 is larger than 12.5, therefore this will be a failure. Now let's explore the metered flow situation, 2 cases. In this case, the conveyor belt is functioning as a feeder conveyor beneath a hopper, and let's assume that flow is unrestricted. Note that the material handling rate of this conveyor is linearly proportional to the belt speed. So if we're handling 400 tons per hour at a belt speed of 50 feet per minute in the conveyor A case, material handling rate will be 800 tons per hour at a belt speed of 100 feet per minute. We need to compare required and available power to drive conveyor A. We need to compare required and available power to drive conveyor B. Let's look at A. If we set the electric power supply rate at 60 Hertz, assuming 460 volt 3-phase 60 Hertz is readily available, and we've selected a belt flow rate of 50 feet per minute to move 400 tons per hour, then an electric motor of 20 horsepower should do the job. Let's compare required and available power. If we install a 20 horsepower motor designed to run at 460 volt 3-phase 60 Hertz, and the power supply is kept at that, then the drive will not fail because required mechanical power, calculated separately, is 15.4 horsepower and available motor power is 20. 20 is larger than 15.4, therefore this drive should work continuously, indefinitely. Now let's see what happens if we want to achieve a flow rate of 800 tons per hour on Conveyor B, keeping all parameters the same, keeping all equipment the same, except that we want to install a VFD. We want to install a VFD so as to set the belt speed at 100 feet per minute to achieve twice the material handling rate. We would be tempted to simply set the variable frequency drive frequency at 120 Hertz. Let's see what power is required. Let's see what power is available. If the installed motor, which I just described in the A case, is 20 horsepower designed to run at 460 volt 3-phase 60 Hertz, and we attempt to change the power supply to 460 3-phase 120 Hertz, the system will fail. Because required mechanical power, calculated separately, is 29.9 horsepower, whereas available motor power is only 20 horsepower. I'll describe later why it stays at 20 horsepower and does not increase. 29.9 is higher than 20, therefore this system will fail. Here's a handy tip to remember when evaluating a belt conveyor drive system in two extremes of belt speed. Does the application require a low torque high speed belt drive system, like a race car? Or does it require a high torque low belt speed drive system like a truck? We'll cover this topic in the next videos. That concludes part 1 of how to drive a conveyor motor with a VFD. We covered an introduction to the topic and learned why a knowledge of relevant rates is important. We hope you found this short tutorial useful. To watch any of the other videos in this series, click one of the links at the bottom of your monitor. To go to our website, click the link in the upper right-hand corner of your monitor now. Thanks for watching.